Okay, this is Chapter 10, Part 3, the confidence interval. And we're going to use an analogy here. Um, and the name of this game is going to be Capture the Parameter. One way to think about estimating parameters in statistics is to think about trying to capture them. So your mission, if you choose to accept it, is to track down and capture a fly, dead or alive. And I'm going to give you a choice of weapons. You can use a BB gun, or you can use a fly swatter. Here's your question. Which weapon choice would give you the most confidence? Well, let's talk about this word confidence for a minute. What do we mean by confident? Here's a general idea. We are confident in something, whatever it might be, when the outcome is frequently, success. So in this little example I'm talking about, this analogy, capturing the fly would be success. Trying to shoot a fly, so say, hold on. Say there's a fly here. I'll try to draw a fly. So here's my rendition of a fly. So the idea is that if I shoot something tiny like a BB at the fly, the chances of missing that fly are very high. So the success rate for a BB for the BB, success rate is low. So our confidence would be low as well. On the other hand, the idea with the fly swatter that makes it probably for most people a better choice is the idea that while the BB can be thought of as a point, the fly swatter really has area. It's got a larger surface to swat the fly with, so using a fly swatter, I think we would say our success rate would be much higher. And therefore our confidence is also higher. So we got this idea of having a point, the BB, much harder to hit a fly with a BB than it is with something that has area, more area, like a fly swatter. So mathematically, I think we would argue that the best choice, or the choice that would give us the most confidence, is a fly swatter. So that takes us to this next example. We're back to the salmon population again. But this time, let's be more realistic. Sometimes really what we want to do is estimate the population parameter. So suppose here the goal is estimating the population parameter. And I like to think of this again as the idea of capturing mu, because that's really what we're trying to do, is we're trying to capture this parameter value. Now, one way to think about it is like this. So turns out I already know where this data came from. And let's write this down here. Here's our what am I trying to spell? Secret. That's hard to read, huh? Our little secret here is that X is in 35. So for this particular data set, I used rand norm 35, 33, and that's where that data set came from. Therefore, this data comes from a known normal distribution. So when I think about the domain of the population now, and I'm using X on the axis now because I'm actually talking about the fish population, or the weights of individual fishes in the population, and we know in that population there's a true mean, and in this case we know it's 30, and that is mu. So this is what we're trying to capture. Now notice this sample mean from our sample actually missed the mean. So this sample mean failed to capture the true mean. And actually 30.51 is also a point on the axis. And this is corresponding to our x bar value. So if you think about this, the concept of confidence, equaling success rate, trying to hit the mean with x bar, is our success rate here is very low. Our confidence is low because our success rate is low. In fact, mathematically, since the domain of this population is uncountably infinite, the probability that x bar actually equals mu is 0. So what we would say is that our confidence in this point estimate is 0 or 0%. So how can we take, what I want you to think about now is, how can I take, can you think of a way I could take this point estimate and turn it into a fly swatter? Well, the analogy for the fly swatter, of course, the fly swatter is two-dimensional and it has area, and we're dealing on a number line that has a one-dimensional element. But if you think about it, if instead of using a single point as an estimate, I figure out a formulaic way or a process for creating an interval of values, the chance of capturing the parameter goes way up. And therefore the confidence goes up. So chance of capturing mu with an interval is much higher in general. And therefore our confidence would be higher. So confidence in a point estimate is 0%. Confidence in an interval estimate is going to be much higher. So the point estimate, x bar, is like the BB. The interval estimate is like a fly swatter. But what we want to talk about, or what we have to come up with, is a process for developing this interval. So I'm going to create the interval by starting with x bar. And in this case, this is about 30.51. And what I can do to create the interval is add and subtract the same quantity. Now, the other element that's going on at the same time is this idea that we call level of confidence. And here's basically how this idea is going to work. So we have, first of all, with the salmon, we could make an assumption that the sample mean is normally distributed. Okay. And centered on mu, the true population mean. Now, if I want 99, or say 95% confidence, then I want to create an interval that captures 95% of the possible x values. And if you remember, the empirical rule tells us if we go about 2 standard deviations on either side of mu, that's going to represent 95% of these population means. So if I go and take the point estimate, x bar, and add and subtract 2 adjusted standard deviations. Okay, now if we knew sigma, ideally that's what we would use, is sigma. And it turns out, in fact, we technically, and we know sigma just because I know what the sample, I sampled, or what data set I sampled this from. But the other thing to remember is that this is a relatively large data set. So I could also, since I'm pretending like I don't actually know what those parameters are at the moment, since 33 is bigger than 30, I could argue that using the sample standard deviation as an estimate for sigma is okay in this case. And so what we have is a very generic, or a very, excuse me, basic formula here for a confidence interval. The 2 standard deviation means that we have about 95% confidence. So what this 95% confidence means is that 95% of the time, this interval will capture the true parameter value. 5% of the time, it's going to miss. On any individual sample, I won't know if I've actually captured the mean or not, but what I will have is the success rate for the type of interval that I'm using. So let's go back to the calculator here for a second and actually do this calculation. Let's see here. Something is going wrong with my computer. All right. So what I wanted to do here is be able to see, oh, there we go. Very strange. Okay. I want to be able to see the sample mean and sample standard deviation. Excuse me. So what I'm arguing here is that if we take the sample mean, 30.51, and I'll subtract first 2 times the estimated standard deviation, divide that by square root of the sample size. This is the standard error of the mean we're talking about here now. This gives me the lower limit of the confidence interval. And to get the upper limit, all I need to do is add, change the subtraction to the add to addition here, which, let's see, let me get back where I need to be. So we're 95% confidence the true mean is somewhere between, say, 27.4 and 33.5. And this is approximately 95% confidence. Now, I'm saying approximately because 2 standard deviations actually is a little bit bigger. So our confidence level for this interval is slightly higher. So the confidence is slightly higher here, higher than 95% here. All right. And sometimes the width of the interval is really important. So notice this interval is a tiny bit wider than it needs to be for 95%. So another way to think about this, okay, and what I want to, and then what I labeled the axis wrong here. I put an X, but I meant to put a Z. Because right now I want to talk about the Z distribution. And one of the reasons why we're looking at Z here is because the Z statistic is the number of standard deviations. So really what we want to do is figure out what are these Z values, I'll call it Z star and negative Z star, that corresponds to a 95% area. And we'll calculate those in a minute. But the other thing I want to point out is that we can make a more generic kind of a formula, because notice these z's here, they can move back and forth. And as I move the z's in and out, what's going to happen to this area in the middle? As the z's go in, area goes down. As the z's go out, area goes up. So we could think of a general form of this confidence interval to be more like x bar plus or minus z star. This is what we call the critical z value times sigma over the square root of n. And this is going to give it, now the percentile, the confidence level is what's going to, how we're going to calculate z star. And we're going to think about this in terms of a percentile. So this z star, the way I'm drawing it here with a 95% confidence, now remember that leaves 2.5% in each tail. Okay. So if I think about the area accumulating all the way up to that z star value, then we would say, in this example, z star is equal to the 97.5th percentile. Okay, and there's actually a percentile option on the calculator for a normal distribution. So what we can do, what I'm going to do is show you how to actually calculate that z critical value. Second bars takes us to the distribution menu, and we're going to use inverse norm. Okay, inverse norm gives us the percentiles. 97.5 is the percentile, and this is for the standard normal distribution. And so what we end up with here, whoops, let's see, what did I do wrong? Oh, I can't put this in as a percent. I got to put it in as a decimal. 0.975. Okay, let's try that. Okay, so what it's telling me is that the actual z star value is more like 1.96. So the way the more refined confidence interval, and by the way, we're going to call this the z interval. Okay, it's going to be the point estimate, x bar, plus or minus, in this case, since we're at 95%, it's going to be 1.96 times the adjusted standard deviation, or the standard error of the mean. So this is the formula, and the general formula, again, is x bar plus or minus. Well, for 95%, I can just put in that critical z value, and in general, that's going to be sigma over the square root of n. But this z star value right here is going to be 95% confidence, because that is this is the 97.5th percentile of the z distribution. Okay, and that's not going to change. If the confidence level is 95%, that value is going to be the same. Of course, sample size and the standard deviation can change for sure. But the most general, okay, so the in percent confidence interval, okay, the most generic form of this formula is going to be x bar plus or minus z star, or critical z value, times sigma over the square root of n, where z star is the nth percentile of the z distribution. That's the most general case. Now, let's talk about the more realistic situation. Okay, here's yet another formula that we can use to calculate or to create a confidence interval for the mean. Notice here what's happened is that multiplier changed from Z star in the formula I had before, change that to T star, and what we have is the T interval. Now remember, the T statistic, this is again the whatever the level of confidence is, this is the percentile for the T distribution with the appropriate degrees of freedom. You remember now the T distribution has fat tails, which means that T star value is going to be inflated, especially when the sample size is large, meaning we're going to have a wider interval when we use a T interval than a Z interval in general. But the really important thing to notice is that instead of sigma in here, now I have S. And what are the assumptions? Well, it says the assumptions are given right here. The interval is based on the assumption that the data are from a random sample. Normal populations are the assumption, but see here, unknown population standard deviation sigma. Now, again, if the sample size is large, this assumption of normality is not so crucial because the central limit theorem kicks in. But if there are outliers, then we're going to have to be even more cautious. Now, terminology-wise, that this quantity right here that we're adding and subtracting to the sample mean is what we call the margin of error. So let's take a look at an example here. So here's what we're given. A beverage dispensing machine is calibrated so that the amount of beverage dispensed is approximately normally distributed with a population standard deviation of 0.15 deciliters. Okay, so sigma is given here. That means we can use the Z interval. And let's see, what else are we given here? So the sample size, let's see, sigma is given. So sigma is 0.15 deciliters. The sample mean is 2.25 deciliters. And the sample size is 36. Now we're asked to find the 95% confidence interval. Okay, and this means that Z star in this example is 1.96, and that's because this is the 97.5th percentile of the Z distribution. So the confidence interval, now the formula is x bar plus or minus 1.96 because we're doing a 95% confidence interval, and that's times sigma over the square root of n. So 2.25 plus or minus 1.96 times 0.15 divided by the square root of 36. Now we could put all of this into our calculator and do the calculation. Turns out the TI has a built-in feature to do this. All right, let's see. Okay. So we go to Stat, go over to Test. Now start scrolling down, and what you'll begin to see are some intervals. Number 7 is the Z interval. So I'm going to select this. We're given statistics, so I'll choose the statistics option. Now the sample mean was 2.25. I picked T interval. Oh, hold on a second. Let me back out of here. My arrow must have, I'll just push number 7 now. Okay, let's try that again. So sigma's given, that's 0.15. Sample mean, 2.25. Sample size, 36. Now notice I can adjust the confidence level here. Right now we're at 95%, which is what the problem's asking for. Press enter. Here, excuse me, here's the interval. It's about 2.2 to about 2.3. So we're 95% confident. Well, let's see here. Let me double check that. Did I get that right? It's about 2.2 to 2.3. Yeah, that's what it is. Okay. So about 2.2 to about 2.3. And so what we want to be thinking about here is, okay, we've got a scale. And mu is unknown. That's what we're trying to estimate. And mu is going to be some point on this x-axis. Well, I don't know which point. I still don't know which point, even though I've calculated the confidence interval. Now, what we've done is we've carved out a little interval of values here on the axis. And what we're saying is we're 95% confident mu is between these values. Okay? Now, there's an interesting mistake a lot of people make here. It's false, actually. It's false to say there's a 95% probability. And part of this is because the probability that the true mean is in here is either 0 or 1. Because in fact, the mean is either in between these values or the mean is outside of the interval. It's one or the other. They can't, there's no, like, and again, once you have the interval calculated, it doesn't make any sense to say there's a 95% chance that the true parameter value is in the interval. So that's why we call it a confidence interval instead of a probability interval. And there's a lot of examples like that in statistics where instead of using the word probability, we have to use something like confidence. And really, when we want to, the best way to think about the confidence level, okay, when we're interpreting, confidence level equals the capture rate. Okay, this is, I think, a good thing to remember, because what this implies is 19 times out of 20 attempts, the parameter is captured. So again, if we're thinking about capturing flies, if we set our confidence level for our fly capturing process is 95%, it means 19 times out of 20 we capture the fly. One time, fly gets away. So if you think about it, you could say there's a 95% chance we'll kill the fly before we attempt it, but once we attempt it, we either did or didn't. And that's why it makes no sense to say there's a 95% chance we killed the fly in past tense. Same thing's true with the confidence interval. So it's a subtle thing, okay? Now, the margin of error here, it turns out we can actually calculate fairly easily. And one of the ways we do that, we know we were given x bar, that was 2.25. And then the interval that we used to estimate or to capture the parameter, according to the formula, okay, the endpoints of this interval are captured by adding and subtracting the margin of error. So if I want to calculate the margin of error, one way to do it from the confidence interval is just to take the 2.3 minus the 2.25, and that gives us 0.05. So 0.05 would be the margin of error. Of course, there's also a formula we can use. And the formula we can use looks like this. The margin of error is the z star value times sigma over the square root. Now this is supposed to be square root. So again, my screen captures have this notational flaw. I don't know why, but something to do with the program, I suppose, or the format of the file. But in any case, it should be a square root of n. So the other way we could have calculated this is to use this formula. Oh, wait, this is for the sample size. Okay, we haven't talked about that yet. So now, another thing we can do, and sometimes one of the things that that's necessary when we're getting ready to do some statistical analysis, is figuring out what size of a sample we need. Okay, so the idea here is that if we're given or told that what the margin of error needs to be, okay, so the question is, how large of a sample would you need if the margin of error is 0.02? So we're told that E is 0.02. So we know 0.02 is going to equal Z star times sigma over the square root of n, okay? And Z star we know because our confidence level is 95%. And sigma was given to us. So what we end up with is this equation to solve. So if we do a little algebra, square both sides, we can get an estimate for the necessary sample size. Let's see. So let's do the calculation and figure out how big this sample needs to be. So we got 1.96 times 0.15 divided by 0.02 whole quantity squared. So we're going to round that up. So we need about 217 samples to meet these parameters that we've been handed. Let's go back and talk about this pH problem again. And because this is even more, I think that, you know, if you think about it, rather than figuring out or doing a hypothesis test here, another way to go about this, or another way to think about this type of a problem is, can we actually use the data instead of figuring out or doing a hypothesis test, right? Instead of figuring out whether the field is neutral or acidic, the other thing we can do is estimate the mean pH. Okay, so a little bit of a different thing. And when we're talking about mean pH here, we're talking about estimating mu. Now, this problem is one of the reasons I wanted to do this problem is because the assumptions here are different than in the previous example. The assumptions, now n is 1, 2, 3, 4, 5. N is 5. This is a small sample. Okay. And also, sigma is unknown. So we're not given sigma here. So these things together tell me I need, instead of a z interval, I need to do a t interval. Okay, if I want to estimate the pH. And so the formula is going to look like x bar plus or minus t star now times s over the square root of n, or the standard error of the mean. But the t-interval is also built into the calculator. So if I go back to the calculator here for a minute, and let's see, I think I might still have that data in my calculator. Let me have a look here. I'm going to check L1. Yeah, I still have the data in my calculator. So, okay, so if you go to stat and to tests, and you scroll down a little bit here, after z-interval, there's oh, I went right by it. There it is. Right after z-interval, there's t-interval. And this time I have data, so I'm going to select data option here. The list is L1, so that's good. We'll leave that the same. And then we need, let's say we do this instead of a 95%, let's say we do this at 99%. So we'll have a higher confidence level, and now we'll calculate. So whoops, oh darn it, hold on now. So our interval estimate for the pH is between 5 and 7.3. And I could say 5.0 here. So one of the other things that now, and I did this at 99% confidence, right? Okay. Now, remember when we did this as a hypothesis test, our p-value, if I remember right, was about 6%. So notice in this example, 7 is within this interval. So mu equals 7. So that was the null hypothesis, is that the soil was neutral. So notice this interval is including 7 as a possible estimate for the true mean. So this is how we can use an interval to do a hypothesis test. If the hypothesized parameter is in the confidence interval, then there's no evidence that we should reject the null. On the other hand, if the parameter value were, if the whole interval were above or below the hypothesized value, then we would have evidence to reject the null hypothesis. Okay, so that's it for part 3, and hope you're having a good day. See you next time.